The more bits in a sequence, we can represent more characters. We can then assign a number to each character. It turns out that a sequence of bits is the same as a number written in base 2 or binary. We talked about that earlier and said we'd explain it later. Well, it's now later. What is binary? People do math using the decimal or the base 10 system, probably because we have 10 fingers. Base 10 uses digits from 0 to 9 to count the whole number of each power of 10 used to make the number. That's a great sentence. Let's show you what it means. Let's say we have this number here, 3,569, which is 3,569. If we break that out, that tells us that we have 3,000s, 500s, 6 10s, and 9 1s. And if we want to make that as powers of 10, here's my 3,000s, right? 10 to the third is 1,000. Here is my 500s. That's 5 times 10 squared. 10 squared is 100. Here's my 10. 6 times 10 to the 1. And you have 6 of them. And this one's a little tricky. Any number raised to the 0 power is just 1. So this one here is 9 1s. You add them all together, and you get this. This is obviously a better way of writing it than all of this, but this tells you where that 3,569 came from. Each digit, 9, 6, 5, and 3, from right to left, remember we're going right to left here, represents the next largest power of 10. Binary, or base 2 numbers, use the same idea. But instead of having 10 digits, like 0 through 9, they only have 2, 0 and 1. We differentiate binary numbers from decimal numbers by ending the number with the subscript 2. So you see here this 1011 subscript 2, that is not 1011. That would be what it is in base 10, but we're in base 2 now. And once again, we'll be reading right to left to go from smallest to biggest. Computers, and here's the key, they do math in binary. Binary is better than base 10 for computers because a 1 can be represented by the presence of a voltage and a 0 by its absence. That's a lot easier than coming up with 10 different measured quantities for base 10. Let's work with a binary number that has 8 bits, and 8 bits is called a byte. So that's 1 capital B, or 1 BYTE, is equal to 8 bits. That's going to be the standard unit for digital information, and we'll get there. So we go from right to left, from smallest to biggest. So we have 2 to the 0. Remember we had that as 10 to the 0, 10 to the 1, 10 squared when we did that thousands number. Now instead of 10 we use 2. 2 to the 1, 2 squared, 2 cubed, 2 fourths. So you can see 2 stays the same. And then below it is what we have in base 10. Okay, now we're given this number in binary, and we know it's binary in 2 ways really. You have the 2 here, that's the definitive way of saying binary. And the fact that all we have are 1s and 0s, that's a clue that we're dealing with binary. So what do? We have our table from the previous slide, and then in the middle one we place each of the red digits in the table in order. So we have 100, 100, 100, 100. Then 10, okay? The next thing we do is multiply each power of 2 by the value of the bit below it. So what does that mean? Here's 128. Multiply that by 1, we get 128. Multiply anything by 0, and you get 0. Then, here's 16 times 1, 16. Couple more zeros. And then what do we have? 1 times 2 is 2. Now we just add them together. So we add 128 plus 16 plus 2. And we get 146. So this number here in decimal is equal to 146. Excuse me, my goodness. This is in binary. We take that binary number, and in the decimal base 10, we get 146.